So in the last video, I was covering linear regression using both PyTorch and JAX, and I noticed that a lot of the times I would say things like, and then you call the optimizer.step function, which updates the parameters of the model, but I couldn't go into detail what that actually meant or what was happening under the hood. So in this video and the next one, I will try to remedy that by giving a detailed introduction into JAX and PyTorch, because we will definitely need a baseline understanding of both of these libraries before we can understand more complicated machine learning models. So in this video, I will do a JAX 101, and in the next one, I will cover PyTorch. So what is JAX? JAX is a machine learning library that started out as the autograd library, which was designed for Numpy and it handled automatic differentiation, and then later grew into JAX as some of the core development team moved to Google, and now JAX is owned and developed by Google. And one of the core features of JAX is that it handles automatic differentiation very well. It works on GPUs and TPUs, since it's owned by Google, and also CPUs. And it follows the functional programming paradigm, which is definitely something you will have to get used to. One more thing I would like to mention is that since JAX is owned by Google, you are at the mercy of Google that they don't randomly shut down the entire project. There's an entire website out there dedicated to products and services that Google has terminated, even though they were highly successful. So that's always something to keep in mind. Personally, I think it's highly unlikely that they will shut down JAX because it's powering the latest LLMs, but it's just something you will have to keep in mind. PyTorch, for example, does not have this problem. They started out as a project from Facebook, and Facebook later gave the project to the PyTorch Foundation, and now they're managing it, and therefore it's highly unlikely that PyTorch will ever go away, but you don't have that certainty with Google. It's just something to keep in mind. I don't want to freak you out that JAX will disappear tomorrow, but you just have to know about this. So with this introduction out of the way, we can now get started. So the first thing I would like to mention is that JAX has their own implementation of the Numpy API, which you would usually import like this. And for the most part, I would say 95% of what you can do in Numpy, you can also do in JAX, and also run that on accelerated hardware like GPUs or TPUs. So if you are very proficient in Numpy, you should feel right at home using JAX. So you can do things like creating arrays like this, and then you would get an array. And you can do something similar in JAX using the JAX Numpy module. And this looks very similar. You can also use other Numpy functions, like for example, computing a dot product. And you can do the same in JAX. So as I mentioned before, JAX has, I would say, 95% the same API as Numpy, but there are some exceptions, specifically when it comes to indexing and RNG. So in Numpy, you would create an array like so. And if you try to update, let's say, the first index to a different number, you would do something like this. And as you can see, you updated the first position to -1, but you cannot do the same in JAX. Watch what happens if you try anyway. And as you can see here, we get an error saying that JAX arrays are immutable and do not support in-place item assignment. So it actually tells you here what to do, but we actually cannot see because the error message is cut off here. But basically, you would use the addSet method. So you would do this instead. So let me clear this. So instead of assigning it like this, and this is wrong, so let me comment this out, you would say x at index 0 and set that value to -1, and then return another array and set it to x. So when you run this, you get no error, and let's see what we get in our array. And as you can see, the first index is now -1. And this is an example of functional programming. In functional programming, you cannot do something like this because everything is immutable, so this would not work, and therefore you have to reassign the array to a different value. So actually this part right here, the set method, as you can see, returns an array, and you assign this to the array right here. So when it comes to random numbers, if you wanted to say a random integer using Numpy, you could do something like this. And sure enough, you would get a random integer. And this is actually a built-in Python integer and not a Numpy array. But if you wanted to create a random number using JAX, you need something which is called a key, or specifically a random key. So to create a random key, you can do this and give it a seed. If we have a look at what this key is, we can see that JAX has returned us a key array. And this key array contains two numbers, and this is already very deep into JAX internal territory, but basically the first number you see there is a unique identifier for a stream, and the second number is the number that you pass here. But usually in your day-to-day JAX usage, you actually don't really care about the first number. You mostly interact with this number, which is the seed that you pass to this key. And now that you have this key array that JAX has returned to you, you can use this to create a random number. And when you do this, you get a random number, but this is not a built-in Python integer, but instead you get a JAX array. But watch what happens if we reuse the same key once more. As you can see, we got the same number again. And the reason for that is that we're using the same key again. So if we want to have a different number, then we need to split this key, and that's the terminology that we use in JAX, to get a new pair of keys, and then use the new pair to generate another random number. So in other words, you would do this. And when you run this, you can see that you have two new keys, where this key is now, I don't know what this number is, but a different number than what we had before. And the sub key is also a different number, or more specifically a pair of numbers. So what happened now is that after we used this split method, we got a completely new key and a completely new sub key. And now that these numbers are different than what we had before, which was 0 and 42, if we use these keys now, we will get a different number than what we had before. And now it's 53. One more thing to note is that you can create more than one subkey. For example, if you needed 50 subkeys because your neural network is 50 layers deep or something, you could do this. And here you have to pass in the number of subkeys you want and then add one more of it. In our case, we wanted 50 subkeys. So the first key will go here, and then the remaining 50 keys will go into this list. So if we run this, you can see that we have 50 subkeys. In Numpy, you could also set a random seed like so. And as you can see, if we run these 3 lines, we keep getting the same number. But in JAX, this wouldn't work as far as I understood because of how JAX handles their internals. But also this kind of goes against the whole principle of functional programming, where you expect the same output given the same inputs. But in this case, you change some kind of global state, and unless you knew about it, you would be confused why your functions start to give different outputs even though you passed in the same parameters. In this example, everything that you need to generate a random integer is given here as arguments, and you will always get the same output given the same input. But it's actually not the case here because you change a global state. So to summarize, JAX handles random numbers using a random key, and the way you get them is using this key function. In previous versions, they didn't use this, so this is actually kind of new, but if you have a look at some older JAX code, you will come across this. And this is the old way of generating random keys, and you will see in the documentation that it says that this is already deprecated and that you should be using this function instead. But once you have this key, you just have to pass it to the function that requires randomness. And that's how you handle RNG in JAX. The main idea here being that you get great reproducibility since everything you need is given here in the arguments and there is nothing hidden from you. But this comes at the expense that you have to handle these keys and then have to keep splitting the keys in order to get a new random number. I had a lot of occasions where I forgot this and didn't quite understand why my program wasn't working until I realized that I kept using the same random key. But this is how you handle randomness in JAX. And now let's get to the VMAP function. I initially thought I was going to show this on screen, but I figured it's actually easier to explain it on pen and paper instead. So let's imagine we have a function f that gets as input x and then returns some numbers in one dimension. And the input x needs to be one-dimensional. For example, because we're using the jmp.convolve method, which requires its input to be one-dimensional. If our input here was anything but one-dimensional, then this convolve method method would fail, and then we would get an error. So in other words, our input x must have the shape n. And we also have our data set, which we denote as capital D, and our data set has d rows, and each row has the size n. So in other words, we have a matrix like this, where each row of the matrix is of size n. So in other words, our function f works on individual rows of the data set like this, but it does not work on the entire data set. So if we gave our function the entire data set as input, we would get an error because the data set has the shape d by n, and our function expects the input to have the shape n. For example, here, if we take the first row, which has the shape n, then this would work. For the second row, it would also work, but it would not work for the entire data set. And there are two ways to handle this situation. Either you can rewrite your function and make it work with the entire data set. For example, we could give it the entire data set, and then you would iterate over each row, apply your function logic on each row, and then put it in a list maybe, and then turn that into an array and then return that. But that is not the JAX way of doing things. In JAX, you can abstract away the batch size. So what I mean by that is, while this is our entire data set, you typically in machine learning split your data set into chunks or batches, and then give those batches to your model. And then your model would handle the batch size. At least that's how you would do it perhaps in PyTorch. But in JAX, you abstract the first dimension, the batch dimension, away. And the way you do that is using the VMAP function. So the VMAP function requires, well, an input function that needs to be applied on your data, and it also can take the in-axis and out-axis as additional input, which are 0 by default. What happens here is that jax.vmap, if we just give it the function f as input, then VMAP returns another function that you can call, and that function that this VMAP returns, we call that function and we give the data D as input. What in-axis refers to is the input axis that you want to apply your function across. In this case, we say that the in-axis is 0, it is 0 by default, and that means we apply this function across this dimension. So 0 refers to the 0th axis of your dimensions. So in other words, we apply the function f across this axis. And now out axis says, well, where do you want to put that dimension? By default, it's 0, so it would put this dimension to the 0th position, so it will be right here. You could also say that the out axis, for example, is 1. In that case, it wouldn't put the outputs across this dimension, but rather across this dimension. So the outputs would be columns basically of this matrix. So in other words, if out axis is 0, then you get a d by n matrix. But if you say the out axis is 1, then this means that you put the out axis, which is this, to the axis at index 1, which refers to this because we are using 0-based indexing. And as you can see, this transposes the matrix because it now has put the output dimension at position 1 right here. And what JAX does internally is that first it takes your input matrix and then applies this function across the in-axis that you defined here, which is 0. So in other words, it applies your function on each row and it puts the output in a d by n array because we define the out axis as 0. And as I mentioned before, you can emulate this if you were to iterate over each row of your data and then apply the function to each row and then stack those into a d by n array, then that would give you the same result. But now let's have a look at a different example. Let's say our function takes two inputs where the first input is again x and now we get another input w, and x has the same shape as before and w has also the shape n. And our x input comes of course from our dataset, but our w is a different vector which I've defined here. So it goes from 0 to 9, so it has 10 values in it. And what we want to do is pass this vector as additional input to our VMAP function. In this case, because w and d have different shapes, we have to handle this a little bit differently than we did before. So now we use the VMAP function, we give it our function f as input, and the in-axes now are 0 and none, and we call the function that VMAP returns using our dataset d and W as input. And now the in-axes refer to the dimension, as I mentioned before, that you want to apply your function across. So in this case, we want to apply the function f across the 0th axis, and this one refers to the first argument that you pass in here. So we want to take the 0th axis of this matrix, in other words, this dimension, but we don't want to do the same for W. We pass in none, and that means basically take the array as is and put that into your function. On the other hand, if W had the same shape as our dataset D, then we wouldn't have to define the in-axis like this, because if we just left it as the default value, which is 0, then it would essentially mean that we give our function f each individual row of our dataset and also each individual row of W, if our W had the same shape, of course, but that would be very inefficient in this example, because it would mean that we have to copy this vector D times, and that is not desirable because that takes away VRAM, for example, on your GPU, and you don't want to do that. So when we call VMAP like this, what happens under the hood is, again, you have your dataset and you apply the function across the 0th dimension of your matrix, so along this axis, but you also have your W here, and your function f now gets as input each row of your dataset and also the entire W as is, because we defined none here. And this operation will work because each row of our dataset D has the shape n, and our W has also the shape n, which means that our function will work. So in other words, the input to our function is the rows of D, each individual row, and also this W, and then the output again is another D by n matrix. So now let's run this in our code. So here we have our function, and as you can see, it gets as input x and w, and both of those are one-dimensional arrays. And within this function, we call the convolve method. And if we check the documentation, we will see that it says is the convolution of two one-dimensional arrays, and we will get an error if the input is not one-dimensional. So if we run this code, we can then set up our data set. So here, our data set capital D is just some random numbers, and it has the shape D by n. And here we have W, which is the window, and it has the shape n. So let's run this. And now if you try to run our function and give it our entire data set as input, it will fail because convolve only supports one-dimensional inputs. So what we do instead is we use the VMAP function, and we give our function here as input and define the in-axis to be 0 for the data and none for the window, and the out-axis is 0. And the VMAP function itself returns another function, as you can see here. So we need to call that function and give it our data and the window as input. And if we run this, you can see that the output shape is 128 by 10 or D by n. And if we set the out-axis to be 1, then the shape transposes to n by d. And that's how VMAP works. In general, whenever you want to apply a function across some dimension of your array, you should be using VMAP. One more thing I wanted to mention is that you can chain VMAPs together. For example, if your input array had this shape A, B, C, D, then each call of VMAP would peel off one of its dimensions. In other words, after the first VMAP call, the first dimension here is peeled off and you're left with B, C, D. After the second VMAP is just C and D, and after the third one, it would just be D. This is definitely something to keep in mind, that you can chain VMAPs together and peel off one dimension at each time. And since the video is getting quite long, I will split this into multiple parts. So in the next part, we will cover JAX grad, JIT, and scan, and also look at while and for loops, how you would implement them in JAX. And then in the third part, we would look at some useful libraries. So I hope you enjoyed the first part of the JAX introduction. Thanks for watching, and I will see you in the next one.